One might think that when the size of a metal particle becomes much less than the wavelength of light, that there would be no interesting interactions between the light and the metal particle. This is not so. It turns out there is a host of interesting interactions that become size independent when the particle itself is much less than the wavelength of light. These arise from the plasma resonance of the metals. In problem 7.4 at the back of chapter 7, which I urge you to do now if you have not done it before, we ask you to consider what happens when a small or a metal particle polarizes spontaneously as a result of a fluctuation of the electron cloud in this direction. So here are excess electrons, here an excess nuclear charge. We use Gauss's law to relate the electric field at the surface to the net charge on the surface. This then gives a force on the electrons proportional to this electric field, pulling them back into the material. And by using Newton's second law for the displacement of charge, which I will call d here, one then arrives at an equation whose solution is simple harmonic motion at a frequency omega p, of course an angular frequency 2 pi f, which is given by n, the number of electrons per unit volume, times their charge squared over their mass times the dielectric constant of free space. For a small particle, one would like to model it as a sphere, so I show on the slide the Lorentz formula for the polarizability of a dielectric cavity in this case. So the formula is written down for some material here in which the outside relative dielectric constant is 1 and inside it's epsilon r. And the way that this problem is solved is to use the boundary condition that the electric displacement field is continuous. When one does this, taking account of geometry, one arrives at this Lorentz formula. Now, a key point to note here is that in metals, electric fields do not penetrate, and then just by analogy to the kappa quantity in quantum mechanics, which became imaginary when one had non-penetrating wave functions, the same thing occurs here. We describe non-penetrating electric fields by having a relative dielectric constant that is negative. Now, it turns out that for silver becomes equal to about 2 at a wavelength of 400 nanometers. Looking at this formula, you can see that a relative dielectric constant of -2, let's put the minus sign in here, leads to an infinite polarizability. So even although the particle may be very tiny, the electric dipole induced by a finite field can become very large indeed. This leads to very strong scattering at the plasma resonance, and also to very strong electric fields around the particle, owing to the induced dipole field. I've also shown on this slide a more general formula derived for oblate spheroids, showing that you can tune the plasma resonance of a particle. Once again, it's purely a material property, doesn't depend on size for a spherical particle, but you can tune this by going, for example, to an oblate spheroid of a ratio of major to minor axes of A over B, and this shows that, for example, for a spheroid of an A to B ratio of 6, that the resonance moves to 700 nanometers. This phenomena could be very useful in building all sorts of photonic devices because of the possibility of greatly enhanced electric field in the vicinity of a small particle. This is illustrated here by an experiment in which this enhanced field is used to enhance fluorescence from molecules in the vicinity of the particle. This effect is controversial because the first order effect of placing a metal close to a fluorescing particle is to quench the fluorescence. When the particle is excited into a dipole excited state, rather than decaying by emitting fluorescence, the first mode of decay in the presence of a metal is to excite energy transfer into image dipoles in the metal that arise because of the large density of states within the metal. So metals usually quench fluorescence. However, if the electric field enhancement is big enough, it can lead to a much larger rate of absorption by the dye. The cross-section of molecules is very small, and this then in turn, because of the principle of detailed balance, leads to much greater fluorescence emission. So is it possible to overcome quenching by a metal with enhanced fluorescence? This experiment shown here addressed that question by using an atomic force microscope probe to hold a gold nanoparticle over a glass surface to which were bound fairly sparsely single fluorescent molecules, which were then excited with a laser field imposed through an objective lens shown down here. Because of the use of an AFM to hold the gold particle in place, this height could be adjusted to see if there was a magic distance at which the electric field enhancement exceeded the effects of quenching in the metal. The answer, at least in this experiment, apparently is yes. Here is a plot of what happens as the laser spot is swept across the surface past a dye molecule. So in the absence of the metal particle is this black line here, and so you see the fluorescence intensity increasing as the laser spot passes over the dye. When the metal particle is placed over the dye, you see that the response is much sharper. Of course, it's not overall higher, presumably because of quenching, but in this region here, where the peak goes over that produced in the absence of a gold particle, there does appear to be significant fluorescence enhancement from the particle. Now, this enhancement arises because of the increase in absorption rate of photons. It's like making the dye molecule bigger, and this means then that, once again, to maintain balance of incoming and outgoing photons, the fluorescence rate must increase with a corresponding decrease in the fluorescence lifetime, or an increase in the decay rate of the excited state. And that is shown here, where time-resolved measurements were made as the laser spot was scanned across the particle. So the hope is that phenomena like these may be used to engineer photonic devices, for example, greatly increasing the electric field at certain points on a device. So, for example, if one had molecules designed to convert light into electricity, and the problem with the molecules was a very small cross-section, then conceivably the judicious placement of nanoparticles could increase this absorption and hence dissociation rate very considerably. The field is still the subject of some controversy and still to reach quantitative agreement between theory and experiment. The thing that has driven this is the observation of absolutely enormous enhancements of the Raman scattering signal that occurs in the presence of small metal particles, but the Raman process is somewhat different from fluorescence.